Ah. Today we're going to look at bonding. We've talked about nomenclature now. Now you can name type 1, type 2, type 3, polyatomic, binary, and acids.
Wow.
How fun is that?
So
Think
fun.
how smart you guys
The
are.
funnest of
The
the
funnest. So now we're going to talk about the Vesper theory. Vesper stands for the valence shell electron pair repulsion. That's what that acronym stands for. Valence shell. So these are the electrons in the valence shell. And it's the repulsion of those electrons. Yes, exactly. They don't like each other. It's kind of like this. It's like these magnets here, okay? The magnets are repelling against each other. They're repulsed by each other, if you want to look at it like that. See how there's space between them? That's a repulsion. That is what the electrons are doing in the atom. They don't like each other. So they're going to try to get away from each other as much as they possibly can. And when they do that, let's see, I have 50-50 chance. Yes. They repel each other. Okay? They are pushing away from each other. That repulsion causes, what?
I got so distracted.
Oh, sorry. That repulsion causes these are different atoms or molecules to take certain shapes. Okay? And don't write all this down. But the repulsion between the electron pairs causes molecular shapes to adjust. They change based on this electron pair repulsion. Okay? They will typically change. And this change gives them certain physical and chemical properties. They are going to try to get far away from each other as they possibly can. They do not like each other. Okay? Now, the shapes I was talking about, there are 5 different shapes. I'll let you finish writing it down if you want to.
It's fine.
I saw some of you guys panic.
I had like 2 words.
Okay. Really, if you just understand the term valence shell electron pair repulsion, it just means that these electrons are trying to get away from each other, and that causes different molecular shapes. Okay? The first shape we're going to look at is linear. Linear shape means they're in a straight line. Carbon dioxide is a linear shape. Okay? Carbon dioxide, this is a linear molecule. Right here. All of the atoms are in a straight line. Okay? Straight line. Just keep following me. Okay? This is a linear molecule, carbon dioxide. See the double bonds here? Okay? They are in a 180-degree angle. They are straight. There. And capture it. Okay? The next one is trigonal planar. It is triangular and flat. That's what makes it trigonal. It has 3 sides to it. What do I do with my trigonal planar? Oh, here it is. This is what a trigonal planar looks like. I'm going to turn on these lights over here. That way you can still see it. This is a trigonal planar. It's got 3 arms coming off of it. So you got that trig, the tri. And it's flat, so it's planar-like. Okay? I will basically give you these shapes and you'll have to identify the name of each of the shapes. Okay? So trigonal planar looks like this. I'm showing the people at home.
Hi, I hope you feel better. I should skip school.
Okay. Then the next one is called tetrahedral. Tetra means what? 4. So it has 4 arms coming off of it. This is carbon tetrahydride. There's 4 little arms coming off of it. It's like a jack almost. That one arm. Okay? So this is carbon tetrahydride. This is a tetrahedral molecule. It's got 4 little arms coming off of it.
What is that called?
Tetrahedral?
No.
Oh, carbon tetrahydride. This is the shape it takes. And then we have pyramidal. Pyramidal looks very much like our trigonal planar. Here's trigonal planar. Here's pyramidal. There's only one difference between these guys. And that is one, the bond angle. I guess there's 2 differences. Bond angle and the fact that the pyramidal has 1 pair of unshared electrons at the top, where the trigonal planar does not. Okay? So here is my pyramidal with the unshared pairs, my trigonal planar with no unshared pairs. So if you look at board up here, if I were to draw my 2, this is one of the molecules, like this. The other one looks like this. It's got a little bit more of a bent shape to it because this guy has unshared pairs of electrons up there. And that unshared pair is, they're trying to get away from each other, so they push down on those hydrogens or the other molecules, like the bonds that are coming off of it, where there are no unshared pairs up here, so there's no reason to push down as much. But here, it's bent a little more because of those unshared pairs of electrons. So when you see the unshared pairs on a 3-pronged molecule, it's going to be pyramidal. Does that make sense? Okay. And then finally, our last one is going to be bent. Yeah. Is bent. I'm just going to move it because I'm tired of trying to. There you go. Whoop. That doesn't say bent. Is bent. The bent molecule is a linear molecule that has unshared pairs of electrons that bend it. So since you have these 2 unshared pairs of electrons, they're all trying to get away from each other, and they bend. They make these guys, instead of being linear, they bend downwards. And that's how you get a bent molecule. And thank goodness this is a bent molecule, because water is a bent molecule. And because it's bent, it gives us all the properties we have to live here on Earth. Does that make sense? Yes? No? So study these. There is a practice test on Schoology. It says practice test for nomenclature and bonding. Make sure you look at it. It's just like the written test you're going to take on Thursday. Okay, so if you can answer the questions on that online test, practice test, you can do it here. Okay? Yes? Okay. Now, so we got our shapes, right? We know linear, tetrahedral, trigonal planar, pyramidal, and bent. Yes? Okay, good. Now let's talk about types of bonds. We know we have ionic bonds where the electrons are transferred, and then you get this positive and negative that are attracted to each other. It's electrostatic attraction. And then you have covalent bonds where they share the valence electrons. There are 2 different types of covalent bonds that we work with. One's called polar covalent, the other is non-polar covalent. We're going to talk about each of these. Okay? So if you haven't written this down, you'll see this again. So we'll talk about polar bonds and polar molecules. Do you need me to go back? Okay. A polar bond is a bond where the electrons are shared. The electrons are shared between the two atoms, but they're not shared equally. Okay? They're not shared equally. One atom is pulling a little bit harder on the electrons than the other atom is. If you look at this tug of war up here, here are my two atoms. This is one atom, this is another atom. And obviously this group, and there's my electrons in the center, if this were my electrons, whoever pulls it closer to them has a greater electronegativity. There's that term again, electronegativity. It's back. Okay? A polar covalent bond, one atom is significantly more electronegative than the other. So in a polar covalent bond, one atom is significantly more polar than the other. It's pulling harder on those electrons. And how do you know which one's more electronegative? Well, if you look on the back of your periodic table, on the left-hand side, right in the middle, you will see electronegativity chart. It will tell you the electronegativities of all the atoms. So if the electrons are not shared equally, it is a polar bond. So let's look at chlorine. Chlorine has what electronegativity? In the back of your periodic table, look at it for me, please. No, chlorine has what electronegativity? That's its atomic number. 3.0. So chlorine has a 3.0 electronegativity. What's hydrogen's? 2.1. Okay? So he's pulling at 3.0, he's pulling at 2.1, chlorine's pulling harder. So electrons are going to shift towards chlorine. Does that make sense? And when that happens, chlorine becomes a little more negative. Chlorine's going to have a slight charge on it because the electrons are getting closer to it. Electrons are negative. The closer those negative particles get close to that nucleus, it's going to become a little more negative. Just like if you've ever, I don't know about you, but you know, if I go around negative people, not that there's negative people here at the school, but some people sit there and all they want to do is complain about the administration. All they want to do is complain about the students. All they want to do is complain, complain, complain. And somehow you get sucked into it. You know, you're sitting at lunch and I'm like, I swear, this group of students, this junior class is the absolute worst. Can you believe this? I'm like, yes, I know. And all of a sudden you start finding yourself saying things that you don't really necessarily feel, but it's so easy to buy into. I don't know if you've ever been like that. But if you're around someone who's positive and go, this is the nicest group of kids I've ever seen. I'm like, oh my gosh, yes. They are so sweet. You know, you're like, am I bipolar or what? You know, good grief, I'm just, you know. But you tend to morph with your environment, so to speak, right? So if you're around negativity, you become more negative. If you're around positivity, you become more positive. Or if you remove yourself from negativity, you become more positive, right? Same thing here. As these electrons get closer to the atom, they become more negative. Not totally negative because they're not ionic, but they're slightly negative. And these guys are slightly positive. Okay? Now this is a little quick video that kind of shows you this. I won't show you the whole thing, but this kind of shows you a little bit more about electronegativity. Whoop, I lied. Whoop, go backwards. Wait a minute, where's my glasses? Okay, let me hit that instead. There we go.
In this video, we're going to talk about polar covalent bonds. The big idea here is uneven sharing of electrons. We usually represent a covalent bond with a single line connecting two elements to each other. In this single line, there are two electrons being shared, one electron from either atom. It would seem that based on this structural formula that the electrons are being shared evenly. However, this is not always the case. Sometimes we have an element that is much stronger than another element. So it's almost like a tug of war going on between the electrons that are in the bond. Now, since both elements in a covalent bond are going to be nonmetals, they're both going to be pulling on the electrons, so they're going to share. We just might have the electrons spending more time around one of the elements as opposed to the other element. Now, the measure of an element's strength is called electronegativity, and electronegativity is the ability of an atom to attract electrons to itself. Linus Pauling was the one who developed this scale of electronegativity. And his scale puts fluorine as the most electronegative element with a value of 4.0. We can determine if electrons are going to share evenly by calculating something called the difference in electronegativity, or in other words, we'll call it delta E. The delta symbol here, this triangle, means difference in. And so when we calculate delta E, we're going to compare two values or two different elements to each other. Let's try this with HCl, hydrogen chloride. So when we look at the periodic table here, we can see that chlorine has a value of 3.0 and hydrogen has a value of 2.1. So let's go ahead and calculate the difference. So delta E is equal to, we'll usually take the bigger number and subtract that from the smaller number.
But it's absolute. If you do it the other way, it doesn't matter.
0.9. Okay. But what does this mean? Well, generally, if we have a difference of 0 to 0.4, we're going to have even sharing of the electrons. We're going to call this type of bond a non-polar bond. If we have 0.5 to about 1.8, we're going to have uneven sharing of the electrons, and we call this a polar covalent bond. Finally, if we have values that are greater than 1.8, generally we're going to have an ionic bond, and we're going to have one element being strong enough or a great enough electronegativity to steal the electron from the other atom. Now, these are just generalized values, and we can have some variation. Okay, so if we look back at our example of HCl here, we can see that it's going to fall into the polar range. Let's see a structural formula here for HCl. If we do that, we would end up with this for our structural formula, where they're singly bonded together. Now, since the electrons are not being shared evenly, we're going to have something called a dipole moment. And we represent a dipole moment with an arrow with a little cross at the end that's pointing towards the more electronegative element. In this case, chlorine is the stronger of the elements, and so the electrons are going to be pulled closer to chlorine. Now, since the electrons are spending more time around the chlorine atom, it's actually going to be affected by that presence of negative charges, and so it's going to have a partially negative charge. The symbol right here just means partially. Now, since the electrons are being pulled towards chlorine, that means they're being pulled away from hydrogen, and so hydrogen will have a partially positive charge. And so a polar bond means that we have one atom being partially negative and one atom being partially positive. So
okay, so that's all we need. So here's our hydrochloric acid or hydrogen monochloride right now. So again, you have these electrons around it, as shown by the electron dots. And unfortunately, I can't, on this type of PowerPoint, I can't get them to move. But the electrons have moved closer to chlorine, which make hydrogen partially positive and chlorine partially negative. So far, so good? Yes? These are partial, not total. A polar molecule is one that has a charge or a slight charge on one of the two atoms, or one or more of the atoms. So one end of the molecule is slightly negative, another end is slightly positive. Water is a really good example of this. A water molecule looks like this. If I were to draw it up here, here's oxygen, here's hydrogen, And here's hydrogen. Oxygen has what electronegativity? What's the electronegativity of hydrogen, or of oxygen, sorry? This is 3.5. And each hydrogen is what? 2.1. 2.1. So if I look at the difference in electronegativity between these two, it's going to be 1.4, correct? If I take 3.5 minus 2.1, it gives me 1.4, correct? I do the same thing over here. The difference in electronegativity is 1.4. So my dipole would look like this. Because the hydrogens are going to be more positive because the electrons are heading towards oxygen, right? They're being pulled closer to oxygen. And when that happens, that gives oxygen that slightly negative charge, and each one of these is slightly positive. So this end is negative and that end is positive of a water molecule. That gives water molecules a lot of physical and chemical properties. I'd say chemical, well, maybe more physical properties. A lot of physical properties. Okay? So notice I did not do between hydrogen and hydrogen. There's no bond there, is there? It's only where it's bonded. Does that make sense? Okay? Good, good, good. So then, we look at our electronegativity. Electronegativity is that pull of an electron. It's the pull of an electron by the atom. We know that nonmetals tend to have higher electronegativities, and metals tend to have lower electronegativities. If you look at your electronegativity table, you can see that. And we will use the difference of those electronegativities to determine the type of bond. Okay? And remember, if you take 2.1 minus 3, or 3 minus 2.1, it's still going to be 1.4 because we use the absolute values. So far, so good? Yes? Yes, Mrs. Cottingham?
Yes, Mrs. Cottingham.
Thank you, Alyssa.
You're welcome.
May I?
No. Okay.
Go right back. Okie doke. Ready?
Mm-hmm.
Okay. So on your back of your periodic table, you don't have these little dots, but you do see electronegativities. So over here, fluorine has the highest electronegativity of 4.0. Fluorine is the most attractive element on the periodic table. For down here, francium has 0.7, one of the least attractive on the periodic table. Okay? And obviously we don't look at the noble gases because they are not part of any reactions. And it's funny because look down here, they didn't include these either. Okay?
Is there one specific least attractive element?
Wait.
Is there one element that's like the least attractive element?
Francium and cesium are kind of about the same. Yeah. Yeah. Okay. A molecule that has two poles is called a dipole. So we were talking about the dipole moment. So basically this is hydrogen chloride. Hydrogen's a little more positive. Chlorine's slightly negative. And the fun thing is you can actually flip them all. If you put them between like plates, like a negative plate and a positive plate, all of the positives are going to point towards the negative, and all the negatives will point towards the positive plate. So you can actually rearrange, you can arrange these based on magnetic fields, which is kind of cool. Okay, so dipole, di means two, pole refers to polarities, dipole, there's two poles to their molecule.
piece of paper.
Oh, thank you. Okay? So, now non-polar covalent bonds play a little nicer with each other. They share their electrons pretty darn equally. They tend not to have dipoles. They don't have dipoles, actually. Okay? So non-polar covalent, non-polar means there's no poles. They are not polar. They share their electrons pretty equally between them. If they're two of the same element, they are completely nonpolar. They have a electronegativity difference of 0. Like when you have any of these diatomic molecules up here. Iodine with iodine, bromine with bromine. Those are going to be completely nonpolar. They will not have partial charges. Does that make sense? Because they're sharing them equally, neither one is pulling harder, so there's no negative charge or positive charge on it. We good? Okay. So that's nonpolar bonds in an oxygen molecule, which is O2. See how they share those outermost electrons? Nice. Now, one thing you need to know, the shape of the molecule will affect its polarity. Even if it is a polar molecule and it has a specific shape, it will affect its polarity. For example, carbon dioxide. Carbon is 2.5. Oxygen is 3.5. It has a polar bond between them. But because it's a straight line, it's a nonpolar molecule. So since CO2 is linear, it's nonpolar. If water would have stayed linear, it would have been nonpolar. But since water is a bent molecule, it is a polar molecule, which I'm very thankful for. Okay? Any questions so far?
No.
No. Okay. So water is polar because the bond polarities don't cancel each other out because it's bent. So water is a polar molecule. Carbon dioxide is not. With us? Okay. I like this little drawing. See how there's a negative end and my two positive ends? It's a very cute water molecule. So do we understand polar bonds and nonpolar bonds? Now, how do you know if it's a polar bond and a nonpolar bond? If you look on the back of your periodic table, on the middle of the right-hand side, you'll see it says polarity. It tells you if the electronegativity difference is between 0 and 4, it's nonpolar covalent. If it's 0.5 to 1.9, does yours say 1.7 on yours?
Mm-hmm.
Somehow that got mixed up. Change it to 1.9 for me, please. So from 0.5 to 1.9. The test copies say 1.9, so I'm not quite sure what happened there. Okay? Yours says 1 point. Now some people say 1.9, some people don't. I'm not quite sure what's going on.
Does the ionic one say 2.0?
Guys, what now?
Is the ionic one supposed to say 2.0?
Yes. Okay. So it's 0.5 to 1.9 is a polar covalent. Anything greater than 1.9 is ionic. Does that make sense? So that's what you do. You have to kind of look at them. So for example, so if I'm looking at carbon tetrahydride, what is carbon's electronegativity? 2.5. And each hydrogen is 2.1. So 2.1 and 2.1 and 2.1. Well, the electronegativity difference between These guys is 0.4. So each one of these bonds is nonpolar. Does that make sense? Yes? Okay. If I had something like, I'm trying to think about what I can do. Let me see. Find this. My lab, sorry. So if I have a, well, it looks like this. Let's see. Well, it's all. Okay. H and H3. So N, H, H, H. Nitrogen is what electronegativity? 3.0, and each of these are 2.1, 2.1, 2.1. So each one of these are a 0.9 difference, right? So they're all polar, and I would draw my dipoles like this. Right? Yes. Well, I may give it to you and say draw the dipoles on here or something like that.
It's going to be on the test, isn't it?
Yes. Yes. So I will give you the structure. You will not have to draw the structure. Okay? You will just have to. Yes. Yes. Or I may just have you do it between two atoms or something. Okay? So far, so good? Okie doke. Okay, then let's talk about attraction between these guys. Attractions between these. Let's see, I'm going to do this way and this way. How about that? Okay? I don't know if that works either. Let's put them both down. Attraction between molecules. There are two different types of attractions between molecules. And I have a little worksheet to give this for you to kind of fill out as we go through this. Okay? Whole bunch of these for you guys. Oh, good catch, Brett. I'm going to explain it to you first, and then we'll kind of take the notes from there. Okay?
Okay.
I think it'll be easier. So, you look over here. There are two different types of attractive forces. And these are attractive forces. So, if I have, let's see, give me a thought here for a second. Let's do water. So here's my oxygen, my hydrogen, and my hydrogen. Okay? These are called intramolecular forces. Those are intramolecular forces. So if I have another water molecule here, if I have another water molecule here, these covalent bonds are my intramolecular. Intramolecular. They are the bonds that hold the two atoms together. Okay? They're the covalent bond that holds the two atoms together. Then there's another type of force. A force between I'll make them a little dashed. I always make them dashed lines. Between the two molecules. The attraction between hydrogen, which is positive, and oxygen, which is negative, they're attracted to each other. This is what we call an intermolecular force. Intermolecular is between two different molecules. So inter is between the molecules. Intra is between the atoms. Does that make sense? So basically what we have here is we have these forces holding the atoms together, and then forces holding the molecules together. Okay? So, intermolecular attractions are weaker than either the ionic or covalent bonds. Intermolecular are weaker than intramolecular. Okay? So, intermolecular are weak. And they're weak because they're just attractions. They're not covalent bonds. It'd be like me holding my husband's hand and standing there talking to someone else next to me. The inter conversation between me and someone else is not going to be as strong as the bond between my husband and I. Does that make sense? The intra is much stronger of a bond than inter. But the thing is, those intermolecular forces, you don't have to write all this down, but the intermolecular forces give us the physical properties. The melting point, the boiling point, the vapor pressure, evaporation rates, viscosity, surface tension, solubility. Because when these intermolecular, look up here, when these intermolecular forces go away, they become gases. They melt. The attraction between them talks about flow rate. They really like each other, they flow more slowly. They don't like each other, they flow quickly. So all of the physical properties we talk about with these compounds is due to these intermolecular forces. The more tightly they're held, the slower they're going to move. The more tightly they're held, the less they're going to evaporate. The less tightly they're held, the easier it's going to be for them to boil. Does that make sense? Yes? Okay. So, intra is between the atoms. Inter is between the molecules. Yes? And another way to think of it is like this. Interstates go between the states. So if you're on an interstate, you go between the different states. If you're on an intrastate, it only goes within the state. Did you know there's such things called intrastates? I was like, I was just like, I wonder if there really is a thing. So I Googled it, and sure enough, that popped up. Yeah. Well, it's like, why do we drive on a parkway and park in a driveway? I don't understand. So I don't know. Okay? Yes, we good? Okay. So, and we're going to stop there. We'll do the hydrogen bonding tomorrow and finish up this.